So you guys enjoying the show so far? Good conference? Let's hear it. Let's hear it for SysDream for putting this thing on, please, because they are doing an awesome job. Yeah, they're doing great. Now, the bad part is for the next little while, you get to listen to me. And these slides are in a piece of it may sound like a vendor, but none of it is vendor because I am not a vendor. I really don't like vendors. So if you're vendors, sorry about that. And the slides will be available to anybody who wants them, and there'll be more complete versions, so you can just give me your card later, and I'll be happy to send them to you. Now, obviously, one of the biggest problems that we hear about, not only here, but in our lives regularly in our business, is how do we measure security? And somebody does a pen test, and you're secure, right? Right? How do we measure security? And that has been one of the problems that we've had in this field for, well, decades, and I've been doing this for a long damn time. Now, the odd part is we can actually measure, and we give to people at home how well their networks perform. We can measure. Anybody can measure. But in our world, we don't have a whole lot of options right now. We trust the vendor. It seems to work. Okay, that's good enough. We can turn everything off as we should before explicitly turning things on. We can count incident reportings. That's another way. Is security good or not? Well, that's causing APTs that are what, averaging 400 days now to detect? So we're back to trusting the vendor. How many people have had their vendor say to us, trust us, it works really well? And that is one of the problems that we're having. So the premise of what we're doing, and I've been working on for a number of years, is we're using a security model that is 45 years old, that was developed in 1972 by Anderson, and it is called the reference monitor, and I'll show you how that works in a little bit. So some of what I'm going to show you is going to be a little bit difficult because I've got to get through it quickly, and the normal presentation is 8 hours long, but I only have 4 hours to do this, so it's going to be a little quicker. So we need to be looking at a different premise of how to view security. For those of you that were at the debate last evening, we were trying to look at things from a different perspective. So one of the problems that we have in security is we always ask the question, and management says, are we secure? Which is pretty much a meaningless question because it is a binary answer, yes or no. And we all know neither one of those answers is true. So the first thing I want to do is kill absolutism. Get rid of the zeros, get rid of the ones, because when it comes to security, unless the power is off, we are not secure in a conventional way that we understand. The other thing we're going to be talking about is we have this thing that has been used now for 10, 12 years, defense in depth. Let's add a firewall. Let's add another ACL. Let's add another password. And then what happens? Well, the bad guys bypass it, as we'll be hearing more today about social engineering, that the majority of successful attacks begin with social engineering. You don't go after the hard, thick walls. You go around them. You dig under them. You hack the human. So we need to start employing a different thing that I call detection in depth. And I'll explain how all that works. One of the fundamental things that we need to do is introduce the concepts that come from the ICS and SCADA world of feedback, positive and negative feedback, and the concept of OODA loops, which was developed for Air Force fighters in the 1980s. And it's called getting inside the decision loop of your adversary. And it's a concept that we do not employ currently in the majority of installations, whether we're at the coding level, internetworking level, physical level, or in the human interaction process for anything security whatsoever. We also don't use a very simple thing that comes from my old world of the analog engineering called out-of-band communications. And I'll show you a couple cases of where we do use it, but we do not use it enough. Other thing that we do not use in our world is the concept of negative time, which is something that comes from the analog world. And again, the analog world, there are no zeros, there are no ones, nothing is perfect, and nothing is totally horrible. It's somewhere in between. Just like our physical health. Are we all perfect? Well, there is no such thing. And we've been trying to fool ourselves for 5 decades in the world of security. The other thing that we need to do when we talk about security models, we hear people say, well, we need a new protocol. We have to replace TCP/IP. How's that going to work? Let's get rid of TCP/IP and put in a whole new protocol and connect the planet. Is that going to happen? No, we're having a hard enough time moving to IPv6. What do we have, 20% adaptation perhaps? That's about it. And that's been going on for over 2 decades. So we're looking at the problem incorrectly. So what we're going to do is start with some simple math here. And basically this says at the top line, from a protection standpoint, the only thing that we can measure, if we chose to, and we don't yet, is how long it takes for your processes, your detection systems, to detect what they are designed to detect. Any black box detection system, any sort of trigger at the code level, an alarm system, it doesn't matter. It's an abstract concept of detection. Visual, auditory, electronic, doesn't matter. We can measure detection. We know how to do that, and I'll show you how. We can also measure reaction, because I remember in the old days we used to get syslogs that were about this long, and people would say, well, I'll go through it in a few months. And what happens? APTs and major breaches are still occurring because of that. What ends up happening mathematically is if we add together our detection time and reaction time, if we are able to measure it, we now know the maximum amount of time-based exposure that we have, whether we're looking at a confidentiality, integrity, or an availability attack of some sort in any domain. The rule is the same. Our goal in this view of measuring security is to get the sum, the addition of detection time and reaction time, to get as close to 0 as possible, which then would put us, hopefully with some level of advantage, inside of that OODA loop where we have to, as defenders, be faster. Simple concept, be faster than the attacker. That is our entire goal. We're never going to be perfectly secure. We just have to be faster in the analog domain, using time as our metric, than what the attacker is doing. And when we start going through this, you're going to see that every single aspect of what we talk about in IT and security has a common metric, and that common metric is time. When we look at file size, bandwidth, those are all time functions, and we have been tending to ignore them, instead looking and searching for this idealized, perfect 0 or 1 binary answer of yes, I'm secure, or no, I'm not. Now, feedback is a really simple process. The thing on the left is a governor, and the term balls to the wall, it's a very US term, but refers to the balls on that, which are a mechanical governor to control the speed of a train, and it's done with air pressure and temperature. In the middle is audio. When we have a microphone that screeches, that's positive feedback. And the entire goal is to be able to control and manage the level of amplification and acoustic response in order so that you can understand me and you're not just going to be hearing a squeal. And on the right is the electrical equivalent. And every single amplifier on the planet that we have been using electronically for over 120 years uses feedback as a method to control the level of amplification and keep the operation of electrical circuits within specific bounds. And that's what we're talking about when it comes to security. We're not going to have a 0. We're not going to have a 1, but we can bound the problem inside of functional limits that we have not attempted to do. Now, when we look at the SCADA and ICS world, Every bit of that is done with a feedback control mechanism of some sort. Think of it as simple as your toilet. After the toilet is flushed, water comes in. What makes the water stop? The ball cock as the water rises, and it triggers a mechanical switch to tell the water, stop coming into the tank. That is a mechanical feedback system that says, enough water, don't need any more. When you look around the world that we live in the physical world, we have bounded conditions everywhere of acceptable behavior. Because what you will hopefully come out of this with is you will learn that the word infinity is the greatest enemy of network security there is. Because when we look at some of these formulas, if numbers start approaching infinity, that's where we are today. We are today where we do not know how to detect, how to react in too many cases. And it's not implemented correctly in the majority of cases. So this world already exists. The entire Netherlands is protected by the Delta Works, the largest ICS system in the world. Water control, electrical control, distribution, queuing functions, load balancing, every single thing that is involved, especially in the physical world, uses some level of feedback in ICS and SCADA systems. This is the world that we tend to be going towards, and we hear people say big data, big data, big data. And big data means it has to be analyzed, and we have to figure it out. But big data is another example of approximation. It is not absolute. It is not a matter of I am secure or non-secure when I use a weighted network, because a piece of neural network development that is used to analyze big data is called bias. And that bias is preconceived notions, it's assumptions that are modified over time as the network learns. One of the problems that we have with artificial intelligence and some of the neural networks is that we have not figured out yet how to prevent poisoning of the data that is feeding into the bias circuits of the neural networks. But all of this is a combination of feedback and feed forward. So feedback goes backwards to give input. Feed forward gives assumptions to later decision-making processes. This is what we're trying to apply to big data, and we're making, again, an assumption that when the output of a neural network that's analyzing big data says X, that it really means X. And it doesn't mean X. It means X at a very precise moment in time based upon a set of predefined bias conditions that are creating a bounded problem, not absolute at all. So in our world, where do we have feedback? Typical network thing, we got a whole mess of data running every which way, and we're doing our best to control it, and we hear about network segmentation in order to keep HR out of web development, but we're not trying to do a feedback mechanism. We don't have the architecture for it because TCP/IP has a fundamental problem. One wire has both the data flow and the control signal, which allows us then, or the bad guys, to jam the lines. That's what DOS is about. We don't have an alternative right now because the current architecture is that TCP/IP was designed to be resilient, not survive an attack. Resiliency is a dynamic condition which was envisioned for rerouting of data, assuming the control signals were still available. If we lose both data and control signals, then we are DOSed, we're hosed, and the availability function is completely gone. But this is the way we're doing things right now. Now, in the world of OODA, we live and breathe it every single day, even though we don't call it that. And we see it in the military world, and it was called observe, look around you, orient, figure out how it fits within the context of your world, make a decision of some sort, using some decision-based algorithm, and then act upon it. Once you've done that, do it again, and do it again, and do it again. The object is to squeeze that loop in time. And that is what Colonel John Boyd developed in the 1980s for aerial dogfighting between planes that are fighting each other in war. So in kinetic conflict, we understand this concept. We understood it from the Cold War, that missiles took, if we detected a launch coming from the Soviet Union at that time, we had 18.5 minutes to press our button and end the entire world. Otherwise, we lose. So there was a bounded time problem that was solved through what we then called mutual assured destruction. In the marketing world, product world, we all live and breathe this. Somebody comes up with an idea. I got this idea that I'm going to build green furry things because the world needs them really badly. Then I'm going to start contextualizing it and figuring out how to make green furry things that are going to work for my target audience, which is the orientation and the contextualization. Then I make a decision. I'm going to go manufacture 3 million of these things, and then the act is try to go out and sell them. But then you're going to do, wow, they didn't buy as many of those. They want blue furry things and red furry things too. And the loop continues. This is why we have a thing called JIT in the physical world, just-in-time delivery, in order to keep the warehouses empty, but keep the products moving as fast as we possibly can. We live and breathe OODA in every single aspect of our lives. The food in your refrigerator is an OODA loop. Your car running out of gas is an OODA loop. When you start thinking about what you live, normal lives, forget business, every single thing that you do and think about is ultimately a feedback loop. And in some cases, you want it to be really fast. And in some cases, you may not want it to be so fast, but it is a time-based function. So let's take a look at an example, and this is how my bank works. I want to make a wire transfer, and I have an option for out-of-band 2FAs, two-factor authentication. So in this particular case, I'm going to initiate a process, and a pause, negative time, is introduced into it. And suddenly then, an out-of-band signal is sent to me through a path that I've chosen. And I typically like to have it come along on my phone because it's with me most of the time. It'll give me some magic code. And what does that little message say? You have 10 minutes to log in, or 5 minutes, or whatever the policy of the particular bank is. If you don't enter it, suddenly that code is gone, and that entire process, that entire transaction is then revoked. This is the basis of time-based security using a feedback loop with out-of-band two-factor authentication in order to make a go, no-go decision. And this is a simple modification of adding analog functionality into the traditional Anderson model. Now, my wife's car, I hate it because it's all computers, and I've got an old 6-speed with 2 radio stations that still work. But when we're driving a car and they have these new collision avoidance systems, they're really cool. And you get the beeps and the alarms and all that. But when we want to change lanes and you want to make a move on the highway, do you want to trust the collision avoidance system 100%? I argue if you do, you are abdicating all sorts of control and giving up responsibility. So the way the car works and turning lanes should work is, again, a decision, time-based feedback loop. I am ready to change lanes. My collision avoidance system is not giving me any warnings. Does that mean I should not turn my head in both directions to look at it? That is a verification. And when we look at trust factors and the amount of trust that we have in a given quality of action, a quality of a decision, we use a thing called Bayesian probabilistic math in order to see a measurable increase in the validity of that decision-making process in the OODA loop. And this is the way we're going to end up with a lot more crashes because collision avoidance systems are using AI, which is using potentially polluted information as well based upon inaccurate biases. So my argument is, in that case, you need a combination of the collision avoidance system and then a secondary verification, which is a simple Alice and Bob Bayesian probabilistic way of looking at the world. And so cars are doing this, but humans by nature, we're going to start trusting the damn computers entirely too much all over again. The fundamental model that I'm arguing for is a redefinition of what is called a Boolean flip-flop. Boolean logic using an RS flip-flop, which basically is a toggle switch. It's an on and off switch that allows Bob and Alice, normally, to reset an output condition of any process. And the Boolean condition can work in code, it can work in human interaction, it can work in any domain whatsoever. However, it's a digital process. That digital process, being binary in nature, says I'm always in an either-or condition. So what happens then if we put a time-based feedback loop into the decision-making process to emulate the world of what we see in ICS and SCADA systems? Well, if in an authentication process, Alice says, hey, I want this to happen, but because I'm very security conscious, I want to make sure Bob approves of that, and Bob can be a process. Doesn't matter. Bob is an abstract concept. He has X amount of time to approve that process. Now, that could be 3 clock cycles, it could be 3 minutes, it could be 3 days. That's an issue of policy as to how you set the time value for the decrementing clock, just the way that a bank does when it's doing an out-of-band verification for some, in my case, mobile transfers of money, and I've asked for it for enhanced security. This is the fundamental basis by which we can start looking at how to solve a number of our security problems, and I call it time-based flip-flop. And it's a simple, logical circuit that has been around for hundreds of years because Boole invented this stuff back in the mid-19th century. And again, we have adapted it strictly upon a binary decision-making process, which is causing our problems. Now, in the physical world, again, we do this already. You go to your office, open the door, and you may have an alarm system, in which case you have 20 seconds, 30 seconds to run off to the closet and enter in a code that only you know in theory, which shuts off the alarm so the police are not called. This is exactly the kind of model that a time-based flip-flop does in the physical ICS mind space that we are not using in our world. And I'm going to show you how to look at this. Jet engine. This is a typical GE engine. There's over 5,000 detection points inside that engine. 5,000 that are detection loops, and the OODA loops in there repeat 5,000 times a second, generating ungodly amounts of terabytes of information that are then sent into an artificial intelligence neural network in order to optimize performance, in order to save fuel, in order to be able to do predictive analysis of failure. They've got metal fatigue sensors. The kinds of sensors that they use in here are the model for which we have the capability in our field to granularize our detection mechanisms as far as we want. And we don't have to go down to the absolute limit, which would be the equivalent of a cryptographic one-time pad of doing it at every single clock cycle or every single decision. But there are mission-critical points in every operation, be it electronic, human, or internetworking, that have to have, and I'm arguing should have to have, detection in depth. Because what we're doing now with defense in depth just means we're pushing the bad guys around the edge. So one of the things that we can look at is how well are some of our existing detection products working? Now, I know that there's some labs out there and do some testing and things, but from a time-based model, they're not looking at them. And all we have to do, and you can do this on, right now, you can go back and do this with 20, 30 lines of simple code, write a Perl script. And basically, you have known good traffic, you create known bad traffic that the product under review should be able to detect, and once you inject bad traffic into that stream, that should start the detection clock. And what you're looking for is how long does that detection product the black box detection system take to be able to actually react to it and stop the clock? This is a simple limit function. It's a bounded problem. It's going to take somewhere greater than one clock cycle, somewhere less than infinity, and you want that time base to be approaching zero, which is why we use limits in here. And the math is ridiculously simple. T1 minus T0 equals your detection time. So when you have these products, go measure them. We have the capability to do this right now. Now, let's say that I want to have an Alice and Bob situation and I want additional levels of verification of it. I can do a secondary black box verification circuit. Now, based upon the amount of faith that I have in that product, that process, whatever that is, I can assign numbers to it, and there's separate charts on how to configure truth tables and trust tables as to the veracity and integrity of the process that you're trying to measure. And what happens when you go through a secondary verification, and it also works, the same math works for two-factor authentication, out-of-band verification. Suddenly, by using Bayesian probability, we can achieve orders of magnitude additional levels of trust in the processes that we are using. Orders of magnitude, and they are measurable. Now, in a lot of cases, we have to really react. We have something that goes wrong. We have an event that occurs, and we have to do something about it in the OODA loop. So in this case, we have two clocks. The first clock sets the detection mechanism, and it tells me, okay, T1 minus T0 equals my detection time. And then as soon as that detection trigger occurs, we start a second time decrementing clock down to begin measuring until a remediation that is policy-driven and built into the product or the process is actually triggered. Then I can have a simple formula to understand my maximum exposure time. And the exposure time, again, we are trying to optimize as a limit to approach zero by squeezing the OODA loop. And this is a continual process. This is a digital manifestation of an OODA loop for a black box detection system and remediation system. The math is absurdly simple, and you can go build these right now and test your existing environments, whether it's a single product or an entire network-wide process. Doesn't matter. It still works. Now, let's take an example in the world of phishing. We have a huge phishing problem because that's social engineering. People get around it. So we go back to the fundamental reference monitor. And in this particular case, our detection is user clicks on something that has come in through his POP mechanism. So we've got an agent, very, very lightweight agent sitting at endpoint. User clicks. What do? We add negative time. Negative time is a delay. The detection mechanism and the analysis is an external process. And we come from this from the world of AV. Is that file infected or not? Now we have to say, how much time does it take for the vendor to give me some level of confidence that whatever that piece of malware is, or that file is it infected, is it hostile or not? Now, some vendors, and I've never seen them really do this right, they say, oh, it works instantaneously. No, it doesn't. Cannot happen that way. Mathematically, it is impossible. It takes some amount of time. Now, the question that is going to start evolving, because everybody's moving over to AI and neural network mechanisms in order to examine big data, and we're improving this within our detection systems, is if it takes, I'm going to make this up, 1 second to achieve a confidence level of 99%, that would mean that we have 1% potential failure. And if you have 100 emails times 10,000 users in a day, suddenly, shit, that's still really sucks. So we have to look at Six Sigma rule. Six Sigma rule says 3.4 failures per million events. That, for our world, still is awful. because we're dealing with billions and billions of events on every single network. So the existing mechanical concepts that Motorola pioneered back in the, I guess, 1960s of Six Sigma is a reference point, but when you do the math on it, it is not good enough. So in this particular case, how long a delay do we want to have? Well, that's going to really be up to how well that vendor's product performs under a detection, reaction mechanism and measurement that I showed you earlier. Now, if the vendor says, well, in 1 second we have 0.99, we have a 99% confidence factor. In 10 seconds, we have a 99.9% confidence factor. And I'm making these numbers up just for visualization. It becomes an issue of policy. How much faith, how much trust, what is the risk tolerance of the organization for any given process? When you're writing code, exactly the same rules apply. How much confidence do you have? Yesterday we were talking about some of the worst threats to networks aren't necessarily internal. It's the partner networks, it's the inter-networking. It's having faith in the other guy, and suddenly you've given him binary control over your networks because you have given him 100% trust. It's like users. We have trusted users. That doesn't work. We know it doesn't work, but we continue going down that path. So in this particular case, we can enforce and say it takes 100 milliseconds. Is a user going to notice a 100 millisecond difference when he's clicking on an attachment? No. Is he going to notice 1 second? Yeah, maybe not. We can begin forcing the vendors to optimize performance based upon time in order to give us an increased level of confidence in our processes and not have user experience interrupted. Now, when we look at things from a DDoS standpoint, it's exactly the same. Currently, DDoS products tend to sit at the endpoint at the enterprise, and they want to try to stop traffic. And yeah, I get all that. And it sort of kind of works in cases. But there's a much more elegant, optimized solution that does not need TCP/IP to be involved in the process. So in this case, let's say we have an enterprise that suddenly is getting some DDoS traffic, and currently there's a DRI, which is a detection reaction interface, and a reaction module. Now that could be one appliance, it could be two appliances, doesn't really matter. That's currently how we're sort of doing it. But what we're not doing is instituting a feedback loop back to the ISP to automatically say, bounded by time, hey, I'm seeing some funky traffic. Can you stop it for me? ISPs can do anything they want to do. They can stop any traffic they want. They can shape traffic any way they want, and this is about out-of-band communication. Because when we're in a DOS world, we're worried about the data and the control signals going down the same wire, and that's why we get hosed so much. So an out-of-band condition, out-of-band communication path could be another TCP/IP channel. In an upcoming book I've got on this, it shows an entirely new out-of-band reaction protocol to be able to have, don't touch TCP/IP, just create an alternative path for detection, reaction, protocols, and be able to then help control what that traffic looks like. So when we do feed forward and add negative time into it, we have a predictability based upon some sort of black box detection, whether it's neurally operated or not. Do we care if our traffic from our primary hop is delayed by 100 milliseconds? We'll never notice because it just happens to be coming along there. We have introduced negative time in order to allow a detection process to occur prior to us being able to act on it, which is, again, back to the OODA loop. Time-based feedback creates an OODA loop and optimizes it within bounded conditions. And the math, again, is ridiculously simple. So in this case, what we want to do is then have an Alice and Bob condition. I want dual levels of trust in order to be able to increase my confidence in the integrity of the process. And that communication has to be able to occur from the ISP and my primary hop, which is going to be my endpoint entry into my network or multiple entries into my network around the world. Makes no difference. The model is fundamentally the same because the detection trigger begins at delay line, and then that delay line is then reverse toggled through a time-based flip-flop bounded by functional limits and policy tolerance for risk. We expand that out to an out-of-band detection reaction matrix. Now imagine for a moment that every tier 1 ISP talked to each other this way, and then every tier 2 and tier 3 supplier and ISP talked to the tier 1s, and they had a global out-of-band peering relationship. Now, peering relationships at the ISP level are pretty simple. They're not millions to millions. They're 6 or 10. It's a very minimal number of relationships that need to be able to have an out-of-band system communicating with each other. Now, by invoking functional limits, feed forward, and negative time into these by using an out-of-band communication system, what would happen to DDoS if this was invoked globally? Suddenly, DDoS and DOS functions are going to go away because we can institute instantaneous, not instantaneous, that's bad, very fast feedback loops up and down all of the hops. Hey, I'm seeing this traffic. Now I'm seeing it from 3 directions because those are my peering relationships. Tell them all, okay, please shape this traffic for me. Blam. The next one tells the next one. The next one tells the next one. And depending upon the backbone speeds and all of that, we'll be able to communicate, perhaps even identify the source. Now, in many cases, the source is going to be ma and pa with a little tiny machine sitting somewhere in Minnesota, which then will help us begin to identify who is part of these botnets, and the process goes back to the source. This is not difficult to do. I've sat with ISPs, and they're looking at trying to do some test beds on this now, and this is not a product. I'm giving all this away for free. It's some ideas that if we do this, what else can happen with spam? Again, we've got detection mechanisms that should be able to identify what's going on. Web of trust. If we take these concepts that tend to be endpoint-only decision-making processes that we've added AI to, by adding this feedback loop and the OODA process and allowing an out-of-band communication, suddenly we have a true cooperative effort where we're not going to end up with perfect security, but we're going to be able to bind the problem within a tolerance for risk based upon time. So a few things to think about and tenets. This is the fundamental circuit that is going to be used for all of these things because we've been using them in the physical world. We've been using them in ICS and SCADA for a long time. But somehow network security people, we're a shitload smarter than everybody else, and we choose not to do it. Let's learn from where in the physical world it already works. We don't have to modify TCP/IP. We can work with what exists. The existing transfer protocols do not matter because a new protocol for an external out-of-band matrix is what is required to be able to make this work on a global level. We know that static analysis that we've been doing for 45 years fails. We need dynamics. We are in a dynamic world here. Everything is in a synchronous communication mode, and we're treating it as though it's asynchronous in a binary condition. Both assumptions are false, and this is one of the reasons security is not working. Infinity generates chaos. This is known from so many mathematical and engineering disciplines. You have to bind infinity, something greater than 0, something less than infinity, and then you bind it from an engineering viewpoint. We know how to do this stuff. Min-max is where we need to go. We're not going to we should not be allowing binary conditions to continue. We know how to do a lot of this stuff, and there's a few of these assumptions. I say get loopy. Everything that we do in our lives is an OODA loop, except protecting the planet and its infrastructure for some unknown reason. So what can you do? Right now, you can measure your detection process. We know how to do it. You can measure a reaction process. We know how to do it. You can measure your vendor black box detection systems. We know how to do it. You can do it at the coding level when you're developing code. It's not part of OWASP yet. Maybe it should be sometime down the line. But we know how to do this stuff. We know how to compare products once we've got the first 2 or 3 things going up here. We can have vendor comparisons and shootouts based upon efficacy over time, which reduces exposure, which reduces risk, and increases trust factor by the orders of magnitude that are required if we're going to get out of the mess we're in right now. Your vendor's going to be very unhappy with you. Hey, give us all the numbers on how this works under these conditions. Very likely they don't know. A lot of the detection companies I've spoken to go, we don't know, we've never looked at it that way. Why don't you? Well, our customers have never asked. Begin asking. We need feedback. We need OODA. We need the metric of time, because this fundamental abstract model will work in the physical, it'll work in the human, it'll work in the cyber domain at any level of granularity you choose to embed into the process that you're trying to do. That is the concept behind how to begin solving our problems. And you guys have been an awesome audience. We're going to try to get back on schedule. If anybody wants slides or an expanded version of this, which is about 800 slides, let me know, and I will overload your inbox, I promise you. Thank you so much, and enjoy the rest of the conference.
Good.